In this video, we are going to study about the magnetic field due to a long solenoid. Yes. What do you mean by a solenoid? A solenoid is an insulated wire. It is an insulated wire wound over an insulating material in the form of a helix. That is something of the shape like this. This is what is called a solenoid. Something, the wire which is wound in the form of a spring. The shape of the spring is called a helix, or something that is used for the spiral binding. That is a helix. So a solenoid is a wire, an insulated wire wound in the form of a helix or an insulating material like air. Air is a perfect insulator. Mica, ceramic, these are some examples of insulating material for which we use for the winding purpose. Now let me consider that this solenoid carries a current I, and this length L is called the length of the solenoid. Please understand, length of the solenoid is not the length of the wire constituting the solenoid, but it is the length of the turns of the solenoid. Understand that? Length of the solenoid means length of the turns of the solenoid. Now, before we go to the analysis of a solenoid, we have to make two assumptions. So it is very important. That's the reason why I didn't write it earlier. Assumptions, I tell you. These are two assumptions are very important in the understanding of the solenoid. Assumption number one is field inside the solenoid. Field inside the solenoid is uniform and parallel to the axis. The field inside a solenoid is uniform and parallel to the axis. Okay, that is assumption number one. Assumption number two is the magnetic field. Field here means magnetic field. Field outside the solenoid is negligible. Field outside the solenoid is negligible. So please understand these two assumptions very carefully. Field inside the solenoid is uniform and parallel to the axis, whereas field outside the solenoid is negligible. Inside is uniform, parallel to the axis. Field outside the solenoid is negligible. Okay, that's the thing. Now we will discuss. Let me consider that this current is I. Likewise, this current is going in the body here, coming out here, going into here, coming out here, going into here, coming out here, going into here, coming out here. We can find out the direction of the magnetic field using the rules we have learned from the circular coil. So it is here it is into the body, here it is coming out of the body. So the shape of the field line should be something like this. This is the shape of the magnetic field lines inside a solenoid. The magnetic field is directed outwards from here, it is directed into here. So this is what is the magnetic field due to a long solenoid. Now we will discuss about the magnetic field produced by this. Now I am considering those currents here. Here it was going into the board. Here these are directions of the currents of the turns of the solenoid. Here it was coming out of the board. Now let me tell you, this is the axis of the solenoid, so roughly. This is the axis of the solenoid. And here the direction of the magnetic field is likewise. Yes. Now the first question I would like to ask you is, what is the magnetic field in this region? 0. Why 0? Because field outside is negligible. It's not 0, but it is approximately equal to 0. The magnetic field is approximately equal to 0. Okay, now we will construct a suitable Arminian loop to study the magnetic fields produced by this. Yes. Okay, I have considered an Arminian loop like this. So this is A, B, C, D. Now let me take the loop A, B, C, D, A. A, B, C, D, A. A, B, C, D, A. As you can see, A, B, C, D, A. This is a closed loop. A, B, C, D is a closed loop. Now, according to Ampere's law, closed integral B dot dl is equal to mu 0 times the current enclosed by this Arminian loop 1, 2, 3, 4. That is 4 I am saying. 4 is just as I have enclosed only 4 currents. This current is I, this current is I, this current is I, this current is I. These are nothing but the number of turns. So actually 4 turns are enclosed by my Arminian loop. So 4I. If n turns are enclosed by your Arminian loop, it has to be ni. That's the meaning. B dot dl is equal to mu 0 times 4I, right? That is the thing. Now we need to get the value of B dot dl for this loop. So what we will do? What is closed integral B dot dl is equal to? That is integral. I have to take over integration over the closed loop. Integration over the loop A, B, C, D, A. So let us start from A to B. Integral for the region A to B. B dot dl. Question. Here the direction of B is here. The direction of dl is upwards. So the question, okay, let us do it here. I'm just reducing the size for our convenience. Let us write equal to also along with it, underline this. So this is AB, B dl cos 90, right? Angle between B and B is 90 degree, which is equal to 0 plus. Now we will take the next part, that is integral BC, B dot dl. Where is the length BC located? Is it inside or outside? The length BC is located inside or outside? You can see that it is outside. And what is our knowledge about the magnetic field outside a solenoid? Negligible. That means this is 0. Here B is equal to 0. B is equal to 0, so this part is also going to be 0. Now plus integral C to D, right? C to D, B dot dl. Here in this region, magnetic field is directed likewise. Here, dl is likewise. The question, so C to D, right? This is C to D. A to B, B to C, C to D. C to D means it is what I am saying. Angle between, what is the angle between B and dl here? It is BDL, 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 BDL. What is the angle between the magnetic field and the length of the region CD, length of the part CD, length of the part CD, length of the part CD, angle between magnetic field and the length of the part CD, 90 degree, so cos 90. So first time is 0, second time is 0, third time, what is cos 90? Cos 90 is equal to 0, the third part is also 0, plus. Now the last part, integral dA, B dot dl. What is the direction of dA? It is from D to A. Direction of dA, as I write like twice, that means D to A, and the magnetic field is also in the same direction. So which will give you B into L. B into L. Now this is equal to mu 0 into 4I. This is equal to mu 0 into 4I. This is equal to mu 0 into 4I. What is the magnetic field inside the locus of rotation? From here I will write the magnetic field B is equal to mu 0 times 4I divided by L. What is 4? In this case, what is 4? 4. 4 is the number of currents enclosed by the Ampere loop, which is nothing but the number of turns. I told you at the beginning of this discussion. 4 is the number of turns enclosed by the Ampere loop. What is form? The number of turns enclosed by the Amperian loop. Number of turns. So I will write this as mu 0 capital Ni divided by L in general. I told you my Amperian loop is enclosing 4 turns. You may be constructing an Amperian loop in such a way that it has got n turns. So capital N by L. So this is mu 0 Ni. The magnetic field inside a long solenoid is mu 0 Ni, where the term N is called number of, small n is called number of turns per number of turns per unit length. Small n is called number of turns per unit length. Number of turns per unit length. So the magnetic field inside a long solenoid is given by mu 0 small n into I. This is the magnetic field due to a long solenoid. Magnetic field due to long solenoid. Magnetic field inside a long solenoid, and this magnetic field has to be parallel to the axis of the solenoid. Now let us discuss about the next thing, that is field due to a solenoid of finite length. Let me consider a solenoid of length finite. It's not infinity. I am considering a solenoid. Let me consider this is solenoid only. Now I want to find out field with a long solenoid of finite length at a point or its axis. Field with a solenoid at a point on its axis. So I am taking this point P here. Let me take this angle as alpha. Let me take this angle as beta. The magnetic field at the point P is given by mu 0 Ni divided by 2. I am just giving the formula only, the proof is relevant for you. Mu 0 Ni by 2 into sin alpha plus sin beta. Now I will tell you how to arrive at that for a long solenoid. For a long solenoid, where is the ends? Ends are located at infinity. For a long solenoid, alpha is equal to beta is equal to pi by 2. Long solenoid means its ends are at infinity. For a long solenoid, this alpha is pi by 2. We will meet these two lines meet at infinity only for a long solenoid. For a long solenoid, these two meet at infinity. Alpha is equal to pi by 2, beta is equal to pi by 2. Sin pi by 2, 1. Sin pi by 2, 1. 1 plus 1, 2. 2 divided by 2, that is gone. The magnetic field will be equal to mu 0 Ni. This is the answer for a long solenoid. Okay, now we will consider the field due to a toroid. Actually, it is very simple to understand once you understand solenoid. What is a toroid? Okay, let me consider a toroid. Okay, I am going to construct a toroid now. So a toroid is a solenoid wound over a circular frame. The inner radius I am saying to be A, outer radius is B. A toroid is a solenoid wound over a circular frame. Wound over a circular frame. Okay. So a toroid is a solenoid wound over a circular frame. Okay, forgive for my drawing abilities. The question is, if I take a point P here, what is the magnetic field at point P? Very simple. Mu 0 I enclosed divided by 2 by x. If I say this distance is equal to x. What is the charge enclosed by an Amperian loop here? If I construct an Amperian loop here, What's the current enclosed by this ampere loop? Current enclosed by this ampere loop is 0, right? No current is enclosed. So the magnetic field at the point P is equal to 0. Now for my convenience, we will just consider likewise. So there is a current into it. This is the direction of current such that it is going there. So here it is going into these currents are going into out. Okay, sorry, there should be one more. Okay, we just reduce to into out. How many that are going into should come out also. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Wow, I think it has to be. How many into marks are there? That many dot marks also should be there. Okay, now taking a point Q here and constructing an ampere loop passing through the point Q. Tell me, what is magnetic field at Q? Which is equal to mu 0 divided by 2 pi into r. If I say the distance from the center is r, mu 0 by 2 pi r into what is the current enclosed? If this is plus I, this has to be minus I. Plus I, minus I, plus I, minus I, so on. How many plus i's are here? Mu 0 times a capital N plus I on here. So if you have capital N plus I means minus capital N minus I is also there, right? Number of currents going into the board is equal to the number of currents coming out of the board, right? So what is the net current enclosed with that? It is also coming out to be 0. Which means there is no magnetic field at this point as well as this point. Then where is magnetic field confined? That's where you have to understand. So that is what you have seen with the solenoid as well. Now I am taking an ampere loop inside this. Now here I can say if I take a point R here, I can say that magnetic field at R is equal to mu 0 by 2 pi. Okay, I am taking something like R dash. So here we can see that this loop encloses only one type of current, say Ni. Now I will say R dash is equal to average radius. R average. Now this is just like what is 2 pi into R average? It is the length of the loop. So it is number of turns divided by length is number of turns per unit length. You are getting it like mu 0 small Ni. Now we can just understand a toroid likewise. It is a solenoid wound in the form of a circle. What is a toroid? A toroid is a solenoid wound in the form of a circle. And let us finally come to the answer for the magnetic field with a solenoid. The magnetic field B due to a solenoid inside it is, toroid inside it is mu 0 Ni divided by 2 pi into inner radius is A, outer radius is B, A plus B divided by 2. A is the inner radius of the toroid, B is outer radius of the toroid, inner radius. So A plus B by 2 is average radius, B outer radius. A plus B by 2 average radius of the toroid. A plus B by 2 is the average radius of this toroid. And this is the answer we have to get for the magnetic field into a toroid and solenoid inside the terms I will say, or in the circular frame. Taking into consideration the permeability of that also, In that situation, you have to multiply this answer with mu r. Mu r is called the relative permeability. Hope that class is clear to you. Thank you.